We've been talking about the continuity of functions, and we'll finish up in this segment with a discussion of homeomorphisms. Now, a homeomorphism is just a continuous bijection that has a continuous inverse, and we'll find this concept useful later in the course when we talk about topological conjugacy in the context of dynamical systems. So we'll start with the definition of a homeomorphism, then look at an example to see that not all continuous bijections have continuous inverses, and finish up with what's called the homeomorphism theorem, which states that a continuous bijection on a compact set has a continuous inverse and is therefore a homeomorphism. So here's the definition. Let x and y be two metric spaces. We say that a function f from x to y is a homeomorphism if it's a bijection and both the function and its inverse function are continuous. Now before we get to the main result, let's look at an example to see that not all continuous bijections are in fact homeomorphisms. So consider the function f with domain being the half-open interval 0, 2 pi in the real numbers, and the codomain being the unit circle in two-dimensional Euclidean space, where for any point t in the domain, the image of the point is given by the coordinates cosine of t and sine of t. Now you should verify that f is a continuous bijection, but it doesn't have a continuous inverse, because the inverse image of the point 1, 0 on the unit circle is the point 0 in the interval, but any neighborhood of the point 1, 0 on the unit circle also contains points whose inverse image is arbitrarily close to 2 pi. Now note that in this example the domain of f is not compact, and the main result we're going to show is that if the domain were compact and you had a continuous bijection, then the inverse image would have to be continuous. So let's state this result and get to the proof. If x is a compact metric space and f is a function from x to y that is a continuous bijection, then f is a homeomorphism. In other words, the inverse image of f is a continuous function. Now one nice thing about the proof of this result is that it follows almost immediately from results that we've proved in other segments. So let's recall some of these results. We have shown that a function is continuous if and only if the inverse image of every open set in the codomain is open in the domain. We've also shown that any closed subset of a compact metric space is compact. We've shown that the image of a compact set under a continuous function is compact. And we've shown that any compact subset of a metric space must be closed and bounded. And these four results apply to any metric space. So we're going to use each one of these now in the proof of the homeomorphism theorem. Now if f is a continuous function that maps x to y, then we know that its inverse image, f inverse, is a function that maps y to x. And from the first point listed on this slide, we can show that this is continuous provided that the inverse image of every open set in x is open in y, where x is the codomain of the inverse function and y is the domain. Now let's start by observing that the inverse image of f inverse is just f, since these are both bijections. So what we need to show is that for every open set S in x, which is the codomain of f inverse, its inverse image, which is f of s, is open in y. So consider any open set S in x. Now since the complement of any open set is closed, the complement of S is closed. And since x is compact, the complement of S is a closed subset of a compact metric space and must therefore be compact. And here we're using the second result on this slide. Any closed subset of a compact metric space is compact. Now we'll use the fact that f is a continuous function, so the image of the complement of S must be a compact subset because continuous functions map compact sets to compact sets. And here we're using the third result on this slide, that the image of a compact set under a continuous function is itself compact. And we'll finish up by using the fact that a compact subset of a metric space must be closed and bounded, and in particular it must be closed. So since the image of the complement of S is compact, it must be a closed subset of Y. And here we're using the last result on this slide, which states that a compact subset of a metric space must be closed. So we've shown that the image under F of the complement of S is a closed subset of Y. Now note that the image of S under F must be the complement of the image of the complement of S under F. And this follows from the fact that f is a bijection. So just convince yourself that the fact that f is a bijection implies this statement. So since f of sc is closed, the complement of this set, which is f of s, must be open. And this must be true for every open set S in X because we started with an arbitrary such set. So we've shown that for every open set S in X, f of s is open in Y. But since f is the inverse image of f inverse, this proves that f inverse is continuous. In other words, we've shown that if X is a compact metric space and f is a continuous bijection from X to Y, then the inverse function f inverse must be continuous and therefore f must be a homeomorphism. And that's it for this segment.